The story of how humanity came to understand magnetism begins with a mystery felt beneath the fingertips of ancient observers, who first encountered certain rocks that possessed an inexplicable power to attract iron. These naturally occurring magnets, known to the Greeks as lodestones, seem to contain an invisible force that reached across empty space to pull metal objects toward them. The phenomenon was so strange, so seemingly alive, that early civilizations attributed it to supernatural agencies. Some believed the stones contained souls or spirits. Others thought they drew their power from the heavens themselves. Greek philosophers attempted to explain magnetism through their cosmological frameworks. Thales of Miletus, one of the earliest known thinkers to ponder the phenomenon around 600 BCE, he suggested that magnets possessed a kind of life force because they could move iron without touching it. This was revolutionary thinking for its time, even if it sounds quaint to modern ears. The very act of seeking a natural explanation, rather than accepting pure mysticism, represented a crucial step toward scientific thinking. The Chinese independently discovered magnetic properties and put them to practical use even earlier than Western civilizations. By the time of the Han Dynasty, Chinese inventors had created the first compasses, initially used for divination and geomancy, before sailors recognized their navigational potential. These early compasses consisted of lodestone spoons balanced on smooth plates, with the handle always pointing south. The technology would eventually reach Europe through trade routes, though it took centuries for the knowledge to migrate westward. Medieval European scholars inherited both the magnetic compasses from the East and the philosophical speculations of the Greeks. They added their own layers of mystical interpretation. Magnets were thought to possess occult virtues, secret powers embedded in nature by divine will. Physicians prescribed magnetic amulets to cure ailments. Alchemists incorporated magnetic stones into their symbolic systems. The line between natural philosophy and magic remained blurry, and magnetism straddled both worlds. Then came William Gilbert, a physician to Queen Elizabeth I, whose work would transform how educated people thought about magnetism. Gilbert was not content with received wisdom or mystical explanations. He wanted to test magnets systematically, to understand them through careful observation and experiment. Between 1589 and 1600, he conducted hundreds of experiments with magnets and magnetic materials, documenting his findings with meticulous care. Gilbert's masterwork, De Magnete, published in 1600, stands as one of the first great experimental treatises in the history of science. The book swept away centuries of accumulated nonsense about magnetism. Gilbert tested the common belief that garlic could destroy magnetic power and found it false. He investigated claims that magnets could cure diseases and dismissed them as superstition. He examined whether magnetic force could pass through various materials, discovering that it penetrated most substances unimpeded. Most importantly, he developed a comprehensive theory of terrestrial magnetism that would survive for centuries. Gilbert's crucial insight was that Earth itself behaves as a giant magnet. To demonstrate this, he carved lodestones into spheres, which he called terrellae, or little Earths. By placing small compass needles at various points on these spheres, he could replicate the behavior of compasses at different locations on Earth's surface. And the needles aligned themselves according to the magnetic poles of his spherical magnets, just as real compasses align with Earth's magnetic field. This was experimental modeling at its finest, a miniature version of reality that revealed underlying principles. He proposed that Earth's magnetic field caused compass needles to point north and south, ending speculation that they were somehow attracted to distant stars or mysterious mountain ranges made of magnetic rock. Gilbert's Earth was itself a massive lodestone, spinning through space with magnetic poles roughly aligned with its axis of rotation. This was a daring claim that positioned Earth as an active agent with physical properties, not merely a passive stage for celestial dramas. Gilbert also carefully distinguished magnetism from another mysterious attractive force known since antiquity: the ability of amber, when rubbed, to attract light objects like feathers or bits of straw. The Greek word for amber was electron, and Gilbert coined the term electric to describe this distinct phenomenon. He recognized that electrical attraction differed fundamentally from magnetic attraction. Electrical forces could be generated by rubbing many different substances, not just amber. They attracted all kinds of light materials, not just iron. and they could be blocked by interposing certain barriers, whereas magnetic forces penetrated most materials. This distinction between electricity and magnetism would persist for more than 2 centuries before scientists discovered the deep connection between them. For Gilbert and his contemporaries, these were entirely separate phenomena that happened to share the quality of acting at a distance. Gilbert's work represented the dawn of electrical science as well as a revolution in magnetic studies. The period following Gilbert saw incremental advances in understanding magnetism, but no comparable breakthroughs. Natural philosophers constructed better compasses, mapped Earth's magnetic field more precisely, and observed how magnetic declination varied by location and shifted gradually over time. But the fundamental nature of magnetic force remained mysterious. What was this invisible agency that reached across space? How did one piece of iron know that another magnet was nearby? Isaac Newton's work on gravity in the late 1600s both illuminated and complicated these questions. Newton demonstrated that gravity, another force acting at a distance, could be described mathematically with stunning precision. His inverse square law predicted planetary motions with unprecedented accuracy. Yet Newton himself was deeply troubled by the concept of action at a distance. How could the sun reach across millions of miles of empty space to hold Earth in its orbit? How could magnets influence each other without any physical connection? Newton famously refused to speculate about the mechanism, stating, "Hypotheses non fingo," or "I frame no hypotheses." He would describe what gravity did without explaining what gravity was. This tension between mathematical description and physical explanation would characterize physics for the next 2 centuries. Scientists could measure and predict the behavior of magnetic forces with increasing precision, but the underlying cause remained elusive. Some proposed that invisible fluids or ethers filled space, untransmitting forces through direct contact at the microscopic level. Others suggested that particles continuously streamed out from magnets to push and pull on magnetic materials. None of these explanations proved satisfactory. The 18th century saw growing interest in electricity, which could now be generated more reliably through friction machines and stored in Leyden jars, early forms of capacitors. Spectacular demonstrations of electrical phenomena became popular entertainment. Experimenters discovered they could give people electric shocks, make sparks jump across gaps, and even kill small animals with electrical discharges. Benjamin Franklin proposed his famous single fluid theory of electricity, suggesting that electrical phenomena resulted from an excess or deficit of an electrical fluid. His dangerous kite experiment demonstrated that lightning was electrical in nature, bringing celestial and terrestrial electricity under the same theoretical umbrella. Yet electricity and magnetism still seemed unrelated. Yes, both involved invisible forces and action at a distance. But electrical effects required rubbing or chemical reactions to generate, while magnets just were. Electrical forces attracted unlike objects and repelled like ones, but magnetic poles always came in pairs, north and south, inseparable. Scientists tried to create isolated magnetic poles, breaking magnets into smaller and smaller pieces, only to find that each fragment still possessed both a north and south pole. The symmetry was intriguing, but puzzling. The first hint of a connection between electricity and magnetism emerged in 1820, and it came from an unexpected direction. Hans Christian Ørsted, a Danish physicist and chemist, was demonstrating electrical phenomena to his students at the University of Copenhagen. During a lecture, with battery circuits and compass needles scattered across his demonstration table, Ørsted noticed something remarkable. When he closed an electrical circuit, bringing current flowing through a wire, like a nearby compass needle deflected from its usual north-south alignment. This observation might have been dismissed as a distraction or experimental error. Ørsted didn't dismiss it. He recognized that he had witnessed something unprecedented, electricity creating magnetic effects. After the lecture, he conducted systematic experiments to verify and extend his observation. He found that a current-carrying wire acted like a magnet, creating a magnetic field around itself. The direction of the deflection depended on the direction of current flow. The strength of the deflection depended on the current's magnitude and the distance from the wire. Ørsted published his findings in July 1820, and the news electrified the scientific community. Within weeks, But researchers across Europe were replicating his experiments and exploring the implications. André-Marie Ampère in Paris immediately recognized the significance. If electricity created magnetism, perhaps magnetism was nothing but electricity in motion. Ampère threw himself into a frenzy of experimentation, investigating how current-carrying wires influenced each other magnetically. Ampère discovered that parallel wires carrying currents in the same direction attracted each other, while wires carrying currents in opposite directions repelled. He proposed that magnetism in ordinary magnets might result from tiny electrical currents circulating within the material, perhaps at the molecular level. This was a breathtaking suggestion. It meant that magnetism wasn't a separate fundamental force at all, but rather a manifestation of electricity. Permanent magnets contained microscopic currents flowing in aligned loops, creating the macroscopic magnetic fields we observed. This theory faced skepticism because nobody could detect these supposed molecular currents or explain what sustained them indefinitely without batteries or other power sources. Nevertheless, Ampère's mathematical treatment of the forces between current-carrying wires was impeccable. He formulated what became known as Ampère's law, relating the magnetic field around a current to the current's magnitude. This mathematical precision helped legitimize the radical idea that electricity and magnetism were intimately related. While Ampère worked on the mathematical and theoretical implications, other experimenters explored practical applications. William Sturgeon in England invented the electromagnet in 1825, demonstrating that wrapping wire around an iron core and passing current through it created powerful temporary magnets. Unlike permanent magnets, electromagnets could be switched on and off, and their strength could be varied by adjusting the current. This immediately suggested technological applications. Like Joseph Henry in the United States improved electromagnet design, creating versions powerful enough to lift thousands of pounds. He also discovered self-induction, the tendency of changing currents in a coil to induce voltages in the same coil, and mutual induction between separate coils. These discoveries would prove essential for understanding electromagnetic phenomena more deeply and would enable the development of transformers and other electrical devices. But it was Michael Faraday who would make the next great conceptual leap. Faraday came from a poor family and had minimal formal education. He was apprenticed to a bookbinder as a teenager, and his education came from reading the books he bound. Fascinated by science, he attended public lectures by the renowned chemist Humphrey Davy at the Royal Institution in London. Faraday took detailed notes, bound them beautifully, and sent them to Davy seeking employment. Impressed by the young man's enthusiasm and careful work, Davy hired Faraday as his assistant in 1813. Faraday proved to be one of the most brilliant experimental scientists in history. His intuition for physical phenomena was extraordinary, even though his mathematical abilities were limited. Where other scientists wrote equations, Faraday drew pictures and constructed physical models. This apparent weakness became his strength, forcing him to think about physical mechanisms rather than mathematical abstractions. When news of Ørsted's discovery reached England, Faraday was captivated. If electricity could produce magnetism, could magnetism produce electricity? The symmetry seemed compelling. Electricity created magnetic fields around current-carrying wires. Shouldn't magnetic fields create electrical currents in wires? Faraday spent years trying to demonstrate this effect. He placed wires near powerful magnets. Nothing happened. He wound coils around iron rings and tried various configurations. Still nothing. The breakthrough came in 1831 when Faraday realized that it wasn't magnetic fields themselves that induced electrical currents, but changing magnetic fields. When he moved a magnet near a coil of wire, a current flowed briefly. When he stopped moving it, the current ceased. When he moved the magnet away, current flowed again, but in the opposite direction. Similarly, when he switched an electromagnet on or off near a coil, the changing magnetic field induced a current in the coil. This discovery, the electromagnetic induction, was monumental. It revealed a dynamic relationship between electricity and magnetism. Changing electric fields created magnetic fields, as Ørsted had shown. Changing magnetic fields created electric fields, as Faraday had now demonstrated. The two phenomena weren't just related, they were intertwined in a kind of reciprocal dance. Faraday's discovery had immediate practical implications. It explained how generators could convert mechanical motion into electrical current by rotating coils in magnetic fields. It showed how transformers could change voltage levels by using changing currents in one coil to induce currents in another. The entire electrical power industry would eventually rest on Faraday's principle of electromagnetic induction. But Faraday's contributions went far beyond this practical discovery. He pioneered a new way of thinking about forces and fields. Rather than accepting action at a distance as a brute fact, Faraday proposed that magnets and electric charges modified the space around them, creating fields that then acted on other magnets and charges. The field itself became a physical entity, not just a mathematical convenience. To visualize magnetic fields, Faraday scattered iron filings around magnets and observed the patterns they formed. The filings aligned themselves into curves connecting the north and south poles, creating visible evidence of the field's structure. Faraday called these curves lines of force and believed they represented something real in space. Where lines of force were dense, the field was strong. Where they were sparse, down the field was weak. The lines showed not just the strength, but the direction of magnetic influence at every point. This field concept was revolutionary, but controversial. Most mathematical physicists of the era preferred to work with forces between distant objects, using Newton's approach to gravity as their model. They saw fields as useful fictions for calculation, but not as real physical entities. Faraday, lacking mathematical sophistication, couldn't express his ideas in the formal language that would convince his mathematical colleagues. His lines of force seemed like metaphors, perhaps even throwbacks to the invisible fluids and ethers that had cluttered earlier theories. What Faraday's ideas needed was a mathematical champion, someone who could translate his physical intuitions into rigorous mathematical form. That champion would be James Clerk Maxwell, a Scottish physicist who combined extraordinary mathematical ability with deep physical insight. Maxwell encountered Faraday's work as a young man and was immediately attracted to the field concept. He saw that Faraday's lines of force could be described mathematically using recently developed tools from vector calculus. Maxwell began working on a mathematical theory of electromagnetism in the 1850s. His approach was to take Faraday's qualitative ideas about fields and express them as precise differential equations. He treated electric and magnetic fields as real physical quantities existing at every point in space with definite magnitudes and directions. The equations would describe how these fields behaved, how they were created by charges and currents, and how they influenced other charges and currents. The project was ambitious and technically demanding. Maxwell had to integrate known results about electricity and magnetism, including Coulomb's law for electric forces, Ampere's law for magnetic fields around currents, and Faraday's law of electromagnetic induction. He also had to ensure mathematical consistency, that the equations didn't contradict each other or lead to impossible results. As Maxwell worked through the mathematics, he encountered a problem. The existing laws, when expressed as field equations, were almost but not quite consistent. There was a subtle mathematical issue involving the conservation of electric charge. To resolve it, Maxwell added a new term to Ampere's law, which he called the displacement current. This term represented a new way that changing electric fields could create magnetic fields, even in the absence of actual electric currents flowing through wires. The displacement current term seemed like a mathematical fix, a correction needed for consistency. But when Maxwell explored its implications, he discovered something astonishing. The modified equations predicted that electromagnetic disturbances should propagate through space as waves. An oscillating electric charge would create changing electric fields, which would create changing magnetic fields, which would create changing electric fields, and so on in a self-sustaining cascade. These electromagnetic waves would travel at a speed determined by the electromagnetic properties of space. Maxwell calculated this speed using known electrical and magnetic constants, and the result was approximately 300,000 kilometers per second. This number was tantalizingly familiar. It matched the measured speed of light to within experimental error. Maxwell reached a stunning conclusion. Light itself must be an electromagnetic wave. Optics and electromagnetism, previously considered separate branches of physics, were unified. This realization transformed physics. Maxwell had shown that visible light represented just one small slice of a much broader electromagnetic spectrum. If his equations were correct, electromagnetic waves could exist at any frequency, not just the specific frequencies we perceive as colors. Radio waves, though not yet discovered, were implicit in Maxwell's mathematics. So were what would later be called microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. And the entire electromagnetic spectrum lay hidden within those four elegant equations. Yet Maxwell's contemporaries struggled to accept his theory. The idea of waves traveling through empty space seemed nonsensical. Water waves need water. Sound waves need air or some other medium. What did electromagnetic waves wave through? Maxwell proposed that space was filled with an invisible substance called the luminiferous ether. This ether supposedly provided the medium through which light waves propagated. The concept was bizarre but seemed necessary. Without some kind of medium, the mechanical intuition of 19th century physicists couldn't make sense of wave propagation. Maxwell himself never lived to see his theory fully validated. He died in 1879 at the age of 48, the same age at which his mother had died. His electromagnetic theory was still controversial, accepted by some, but doubted by many. The experimental proof would come from a young German physicist named Heinrich Hertz. Hertz wasn't originally trying to prove Maxwell's theory. He was investigating electrical oscillations using spark gaps and conducting loops. In 1887, he noticed something peculiar. When sparks jumped across one gap, they somehow triggered sparks in a completely separate circuit several meters away. No wires connected the two circuits. Hertz realized that electromagnetic waves must be traveling through space from one circuit to the other. He had discovered radio waves. Hertz proceeded to demonstrate that these waves behaved exactly as Maxwell had predicted. They could be reflected, refracted, and polarized. They traveled at the speed of light. They obeyed Maxwell's equations precisely. The verification was complete. Electromagnetic waves were real, and light was indeed electromagnetic in nature. When someone asked Hertz about practical applications for his discovery, he reportedly replied that there were none. It was pure science, satisfying intellectual curiosity, but without obvious utility. Within decades, of course, radio technology would transform human communication. The confirmation of Maxwell's theory brought immense prestige to electromagnetic physics, but it also deepened certain puzzles. If light consists of waves in the ether, then motion through this ether should be detectable. Earth moves through space at considerable speed as it orbits the sun. Surely this motion should create an ether wind, similar to how running creates a breeze even on a calm day. The speed of light should differ depending on whether it travels with or against Earth's motion through the ether. Albert Michelson and Edward Morley designed an exquisitely sensitive experiment to detect this ether wind. Their interferometer could measure tiny differences in light speed along different directions. They performed the experiment in 1887, the same year Hertz discovered radio waves. The result was shocking. No ether wind existed. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. The experiment was repeated many times, under various conditions, always with the same null result. The physics community grappled with this paradox for nearly 2 decades. Some proposed that the ether was dragged along with Earth. Others suggested that objects contracted when moving through the ether, perfectly cancelling any observable effect. Various ad hoc explanations emerged, each attempting to preserve the ether concept while explaining the null result. The true resolution came in 1905 when Albert Einstein published his special theory of relativity. Einstein took a radical approach. He simply accepted that the speed of light is constant in all reference frames, regardless of the motion of the source or observer. He abandoned the ether entirely. Space didn't need a medium for electromagnetic waves. The waves were fundamental disturbances in the electromagnetic field itself, which existed throughout space. This perspective revolutionized physics, leading to profound insights about space, time, and the relationship between matter and energy. But even as relativity was transforming our understanding of space and time, another revolution was brewing. This one would cut even deeper, challenging the very foundations of how we think about physical reality. It concerned the nature of matter, energy, and the strange behavior of things at the atomic scale, and magnetism would play a central role in this quantum revolution. The story begins with a crisis in physics at the turn of the 20th century. Classical physics, including Maxwell's electromagnetism, could not explain certain experimental observations. One concerned the spectrum of light emitted by hot objects. According to classical theory, a heated object should emit infinite amounts of energy at high frequencies, which clearly didn't happen. Max Planck solved this ultraviolet catastrophe in 1900 by proposing that energy came in discrete chunks, or quanta. The idea seemed like a mathematical trick at first, but it worked. Einstein extended this quantum idea in 1905, the same year as his relativity paper. He proposed that light itself comes in discrete packets of energy called photons. This explained the photoelectric effect, where light striking metal surfaces ejects electrons. The effect depends on light frequency, not intensity, which made no sense for waves, but perfect sense for particles. Each photon carried a specific amount of energy determined by its frequency. The wave-particle duality of light created conceptual vertigo. Was light a wave or a particle? The answer seemed to be both, depending on how you measured it. But if light exhibited this dual nature, what about matter? In 1924, Louis de Broglie proposed that particles like electrons should also have wave properties. This audacious suggestion was quickly confirmed by experiments showing that electron beams create diffraction patterns, just like light waves. Quantum mechanics emerged from these strange observations. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others developed mathematical frameworks to describe atomic-scale phenomena. The theory was wildly successful at predicting experimental results, but its interpretation challenged intuition. Particles didn't have definite positions or velocities until measured. They existed in superpositions of multiple states simultaneously. Observing a system fundamentally changed it. And the deterministic clockwork universe of Newton gave way to a probabilistic reality, governed by wave functions and uncertainty principles. Magnetism became a testing ground for quantum theory. Classical physics had never fully explained why certain materials were magnetic while others weren't. Why did iron, nickel, and cobalt exhibit strong magnetism, but copper and aluminum didn't? Why did heating a magnet destroy its magnetism? These questions required understanding matter at the atomic level. Early quantum models of the atom pictured electrons orbiting the nucleus like planets around a sun. These orbiting electrons constituted tiny current loops, which should generate magnetic fields according to Maxwell's equations. This orbital motion did contribute to atomic magnetism, but it couldn't explain everything. But the magnetic moments measured experimentally didn't match calculations based solely on orbital motion. The solution involved yet another quantum property: spin. In 1922, Otto Stern and Walter Gerlach performed a famous experiment. They sent a beam of silver atoms through an inhomogeneous magnetic field. Classical physics predicted that the beam should spread into a continuous distribution as atoms with randomly oriented magnetic moments deflected by various amounts. Instead, the beam split into just two distinct spots. The atoms behaved as if they had magnetic moments that could only point in two directions, roughly aligned with the external field or roughly opposite to it. There were no intermediate orientations. This quantization of magnetic moment couldn't be explained by orbital motion alone. So something else was contributing to the atomic magnetic moment, and that something could only take discrete values. Wolfgang Pauli proposed that electrons possess an intrinsic angular momentum separate from any orbital motion. He introduced a quantum number to describe this property. In 1925, George Uhlenbeck and Samuel Goudsmit gave this property its name: electron spin. The term is somewhat misleading because electrons aren't literally spinning like tiny tops. Spin is a purely quantum mechanical property without any classical analog. But like a spinning charged sphere, an electron with spin has a magnetic moment. Electron spin comes in two varieties, often called spin-up and spin-down. These represent the two possible orientations of the electron's intrinsic angular momentum with respect to some chosen direction. The magnitude of this angular momentum is fixed, but its orientation can flip between these two states. This binary nature explained the Stern-Gerlach result. The silver atoms split into two beams because their outermost electrons could be in either spin-up or spin-down states. The discovery of spin resolved many puzzles about atomic structure and magnetism, but it created new theoretical challenges. How could quantum mechanics accommodate this intrinsic angular momentum? The answer came from Paul Dirac in 1928. Dirac was attempting to formulate a version of quantum mechanics consistent with Einstein's special relativity. The equations he derived had an unexpected feature. They automatically included electron spin. Spin wasn't something added to quantum mechanics as an afterthought. So it emerged naturally when quantum mechanics and relativity were properly combined. Dirac's equation was a triumph of theoretical physics. It predicted the magnetic moment of the electron with stunning accuracy. It also predicted the existence of antimatter. For every particle, Dirac's mathematics implied the existence of a corresponding antiparticle with opposite charge. The antiparticle of the electron, called the positron, was discovered experimentally in 1932. This validation cemented Dirac's equation as a cornerstone of modern physics. With spin understood, physicists could finally explain the magnetic properties of materials. Every electron acts like a tiny bar magnet due to its spin. In most materials, electrons pair up with opposite spins, canceling each other's magnetic moments. Such materials are weakly magnetic at best. But in ferromagnetic materials like iron, nickel, and cobalt, the situation differs. In these metals, the atomic structure and quantum mechanical interactions favor parallel alignment of electron spins within small regions called magnetic domains. Within each domain, millions of atomic magnetic moments point in the same direction, creating a strong net magnetic field. In an unmagnetized piece of iron, these domains point in random directions, so their fields cancel when averaged over the whole material. But applying an external magnetic field can rotate the domains into alignment. Even after the external field is removed, many domains remain aligned, creating a permanent magnet. Temperature plays a crucial role in ferromagnetism. Diathermal energy causes random atomic vibrations that work against the alignment of magnetic moments. At sufficiently high temperatures, these thermal fluctuations overwhelm the quantum mechanical forces promoting alignment. Each ferromagnetic material has a critical temperature, called the Curie temperature, above which it loses its ferromagnetic properties. For iron, this temperature is about 770 degrees Celsius. Heat an iron magnet above this point, and it ceases to be strongly magnetic. Cool it back down, and ferromagnetism returns, though the domains will be randomly oriented unless an external field is present. The quantum mechanical explanation for why some materials are ferromagnetic involves subtle interactions between electrons. When electrons are close together, as they are in solids, so their behavior is governed by the Pauli exclusion principle. This principle states that no two electrons can occupy exactly the same quantum state. Electrons are fermions, particles with half-integer spin, and fermions obey exclusion. The exclusion principle has profound consequences for electron arrangements in atoms and solids. It explains the periodic table structure, why atoms have electron shells, and why some materials conduct electricity while others don't. For magnetism, the exclusion principle interacts with electron-electron repulsion in subtle ways. When two electrons are near each other, they experience electrostatic repulsion. But if their spins are parallel, the exclusion principle forces them to occupy different spatial regions, keeping them farther apart on average. This reduces their electrostatic repulsion energy. In certain materials, this energy reduction is significant enough that parallel spin alignment becomes favorable despite the cost of creating a net magnetic moment. This exchange interaction, a purely quantum phenomenon with no classical analog, is responsible for ferromagnetism. Other types of magnetism exist beyond ferromagnetism. In antiferromagnetic materials, neighboring atomic spins align in opposite directions, creating a regular pattern of alternating spin orientations. The material has no net magnetic moment, but the ordered spin structure still affects its properties. Chromium and manganese are antiferromagnetic below certain temperatures. Ferromagnetic materials have a more complex structure where different types of magnetic ions form sublattices with opposite alignments, but the moments don't completely cancel. The result is a net magnetization weaker than in ferromagnets, but still substantial. Magnetite, the lodestone that started humanity's exploration of magnetism millennia ago, is actually ferrimagnetic, not ferromagnetic. Paramagnetic materials contain atoms or ions with unpaired electron spins, giving each atom a magnetic moment. However, without the strong interactions that lead to ferromagnetism, these moments remain randomly oriented at room temperature. Applying an external field causes a slight alignment, making the material weakly magnetic. Remove the field, and thermal agitation quickly randomizes the moments again. Aluminum, platinum, and oxygen are paramagnetic. Diamagnetic materials exhibit the weakest form of magnetism. All materials are diamagnetic to some degree because the effect arises from the response of electron orbits to external magnetic fields. When you apply a magnetic field to any material, it slightly modifies the electron orbital motion in ways that generate a weak magnetic field opposing the applied field. For most materials, this diamagnetic effect is completely masked by stronger paramagnetic or ferromagnetic behavior. But in materials where all electrons are paired and have no net spin, diamagnetism is the only magnetic response. Water, copper, and gold are diamagnetic. A spectacular form of diamagnetism occurs in superconductors. These are materials that, when cooled below a critical temperature, lose all electrical resistance. They also exhibit perfect diamagnetism, completely expelling magnetic fields from their interior. This Meissner effect, discovered in 1933, causes a magnet to levitate above a superconductor because the superconductor generates exactly the field needed to repel the magnet completely. Superconductivity is another quantum phenomenon. Below the critical temperature, electrons in the superconductor form Cooper pairs through interactions mediated by lattice vibrations. These pairs behave as bosons rather than fermions, and they can all occupy the same quantum state, forming a macroscopic quantum phenomenon. The paired state is so energetically favorable that no electrical resistance occurs. Current can flow indefinitely without energy loss. The perfect diamagnetism arises because any magnetic field penetration would break Cooper pairs at the surface, which costs energy. It's energetically cheaper for the superconductor to generate surface currents that perfectly cancel the external field. The development of quantum mechanics transformed our understanding not just of magnetism, but of all physical phenomena. Yet even with these powerful theoretical tools, many aspects of magnetism and magnetic materials remain active areas of research. Modern physics continues to uncover new magnetic phenomena and find technological applications. One frontier involves magnetic domains and domain walls. Controlling how domains form, move, and reorganize is crucial for magnetic data storage. Hard drives store information by magnetizing tiny regions of a magnetic coating. Each region, representing one bit of data, is a single magnetic domain. Reading involves detecting the magnetic field from each domain. Writing requires flipping domain orientations using magnetic fields from the drive's write head. The physics of domain switching is surprisingly complex. Flipping a domain isn't instantaneous. The reversal propagates through the material as domain walls. Boundaries between regions of different magnetization sweep across the magnetic grain. The speed and reliability of this process determine how fast data can be written and how stable the storage is. Researchers study domain wall dynamics to develop faster, more reliable, and more energy-efficient magnetic storage technologies. Another research area involves magnetic thin films and multilayers. When magnetic and non-magnetic materials are stacked in atomically thin layers, novel phenomena emerge. One example is giant magnetoresistance, discovered in 1988. In certain multilayer structures, electrical resistance depends dramatically on the relative orientation of magnetic layers. If adjacent magnetic layers have parallel magnetizations, resistance is low. If they have anti-parallel magnetizations, resistance is high. This effect is much larger than similar phenomena in bulk materials, hence the name giant magnetoresistance. The discovery earned Albert Fert and Peter Grunberg the 2007 Nobel Prize in Physics, but it also had immediate technological impact. Giant magnetoresistance enabled a new generation of hard drive read heads far more sensitive than previous designs. This increased storage densities dramatically, contributing to the exponential growth in data storage capacity over recent decades. The technology also found applications in sensors and magnetic random access memory. These applications exemplify how fundamental physics research leads to practical technologies, often in unexpected ways. When scientists first studied quantum mechanics and electron spin in the 1920s, nobody envisioned hard drives or medical imaging devices. The researchers were trying to understand nature's basic principles, yet this fundamental knowledge eventually enabled technologies that shape modern life. Spintronics represents the current frontier in magnetic technology. Traditional electronics uses electron charge to represent and process information. Spintronics adds electron spin as an additional degree of freedom. Devices could exploit both charge and spin, potentially enabling new functionalities and improved performance. Spin-based transistors, spin transfer torque devices, and topological insulators are among the concepts being explored. One challenge in spintronics involves creating, manipulating, and detecting electron spin states in practical devices. Generating spin-polarized currents, where more electrons have one spin orientation than the other, requires special materials or magnetic fields. Maintaining spin coherence, keeping electrons in definite spin states as they move through a device, is difficult because interactions with the material environment cause spins to randomize. Reading out spin information requires converting spin states into measurable electrical signals. Despite these challenges, spintronic devices are entering practical use. Spin transfer torque magnetic random access memory uses spin-polarized currents to flip magnetic domain orientations for data storage. Unlike conventional RAM, this memory is non-volatile, retaining information when power is removed. It's also faster and more energy efficient than some alternative memory technologies. Several companies have commercialized spin transfer torque memory for specialized applications, and continued development may lead to broader adoption. Magnetic materials also play crucial roles in power generation and transmission. Generators in power plants convert mechanical energy to electrical energy through electromagnetic induction, the principle Faraday discovered. Moving conductors through magnetic fields, or changing the magnetic field through stationary conductors, induces electric currents. Efficient generators require strong, stable magnetic fields, typically produced by electromagnets with ferromagnetic cores, to concentrate and amplify the field. Transformers, essential for power transmission, also rely on ferromagnetic materials. A transformer consists of two coils wound around a shared ferromagnetic core. Alternating current in one coil creates a changing magnetic field in the core, which induces current in the second coil. By using different numbers of turns in the two coils, transformers can increase or decrease voltage. High voltage transmission reduces power loss over long distances, while lower voltages are safer for end users. The ferromagnetic core guides and concentrates the magnetic field, making the energy transfer between coils efficient. The choice of ferromagnetic material for transformer cores affects efficiency significantly. Iron has high saturation magnetization, meaning it can carry strong magnetic fields before becoming magnetically saturated. However, changing magnetic fields in conducting materials induce eddy currents, circulating currents within the material that dissipate energy as heat. To minimize eddy currents, transformer cores use thin laminated sheets of iron alloys with insulating coatings between layers. This breaks up the possible current paths, reducing energy loss. At higher frequencies, laminated iron becomes insufficient. Ferrites, ceramic ferromagnetic materials composed of iron oxide and other metal oxides, are electrical insulators while remaining magnetically active. This combination eliminates eddy currents entirely. Ferrites are used in high-frequency transformers, inductors, and electromagnetic interference filters. The modern electronics industry depends on these materials for power supplies, signal processing, and electromagnetic compatibility. Magnetic phenomena also extend beyond solid materials into plasmas and astrophysical contexts. The Sun and other stars have magnetic fields generated by the motion of charged plasma in their interiors. These stellar magnetic fields drive phenomena like sunspots, solar flares, and coronal mass ejections. Understanding stellar magnetism requires combining plasma physics, magnetohydrodynamics, and nuclear physics. Earth's magnetic field, mentioned earlier, originates from the geodynamo, a convective motion of molten iron in the outer core. The field reverses polarity irregularly, averaging about 4 reversals per million years, though the timing is highly variable. The geological record, preserved in magnetic minerals in ancient rocks, reveals this reversal history. When volcanic lava solidifies, magnetic minerals within it align with Earth's magnetic field at that time, creating a permanent record of the field's direction. This paleomagnetic evidence contributed to the acceptance of plate tectonics. Magnetic minerals in rocks on either side of mid-ocean ridges showed symmetrical patterns of magnetic reversals. As new oceanic crust forms at these ridges and spreads outward, it records Earth's magnetic field direction. The symmetrical stripe pattern proved that seafloor spreading occurs, supporting the theory of continental drift that had been controversial for decades. On larger scales, magnetic fields permeate the galaxy and intergalactic space. These cosmic magnetic fields, though extremely weak by laboratory standards, play important roles in astrophysical processes. They affect the motion of charged particles, influence star formation, and shape the behavior of interstellar plasma. The origin and evolution of cosmic magnetic fields remain active research topics, with implications for our understanding of galaxy formation and cosmic structure. Neutron stars, the collapsed cores of massive stars, possess the strongest magnetic fields known. These objects pack more mass than the Sun into a sphere only about 20 kilometers across. Some neutron stars, called magnetars, have surface magnetic fields 1 trillion times stronger than Earth's field. Such intense fields dramatically affect atomic structure, stretching atoms into elongated shapes and modifying their energy levels. Magnetars occasionally release enormous bursts of energy when their magnetic fields suddenly reorganize, events detectable across vast cosmic distances, black holes, regions where gravity is so strong that nothing can escape. They can also have associated magnetic fields. While the black hole itself has no magnetic field, the swirling plasma around it generates powerful magnetic fields that help drive relativistic jets, narrow beams of matter and energy shooting outward at nearly light speed. These jets, observed from supermassive black holes at galaxy centers, are among the most energetic phenomena in the universe. From ancient lodestones to neutron stars, from Gilbert's de Magnete to Dirac's equation, magnetism has captivated human curiosity and driven scientific progress for millennia. What began as mystical wonder at stones that moved iron evolved into one of physics' most sophisticated and fruitful domains. Each generation of scientists built on earlier discoveries, gradually refining our understanding while repeatedly overturning previous assumptions. The progression reveals a pattern in how science advances. Initial observations lead to phenomenological descriptions, rules that predict behavior without explaining underlying causes. Deeper investigation uncovers connections to other phenomena, suggesting unified frameworks. Mathematical formalization enables precise predictions and reveals previously unsuspected implications. Did new experiments test these predictions, sometimes confirming theories, sometimes revealing limitations that demand further theoretical development? The cycle continues, with each iteration bringing deeper understanding and broader synthesis. Looking back at how far we'd traveled from those ancient Greek shepherds, noticing their iron-nailed sandals sticking to strange rocks, it's almost overwhelming to consider what remained to be discovered even after Maxwell had seemingly completed the picture. His equations described the behavior of electromagnetic fields with breathtaking completeness, yet they said nothing about why atoms possessed magnetic properties in the first place. That question would require an entirely new revolution in physics, one that would shake the foundations of everything scientists thought they knew about reality. The problem became acute around the turn of the 20th century. Classical physics could explain many things, but atoms themselves remained mysterious. When physicists tried to apply Maxwell's equations and Newton's laws to the structure of atoms, they got nonsense answers. An electron orbiting a nucleus should radiate energy continuously and spiral inward in a fraction of a second. Obviously, atoms didn't collapse, but why not? And what determined which elements were magnetic while others weren't? The answers started emerging in 1900 when Max Planck, studying the light emitted by hot objects, reluctantly introduced the idea that energy came in discrete packets he called quanta. It was a desperate move, a mathematical trick he hoped wouldn't be necessary. But Albert Einstein took it seriously in 1905 by showing that light itself came in particle-like packets called photons. Then in 1913, Niels Bohr applied quantum ideas to atoms, proposing that electrons occupied specific allowed orbits, jumping between them by absorbing or emitting photons of specific energies. It was weird, almost arbitrary, but it explained the distinctive colors of light emitted by different elements. Still, These early quantum ideas were patches on classical physics, not a coherent new theory. The real breakthrough came in the mid-1920s when Werner Heisenberg, Erwin Schrödinger, and others developed full quantum mechanics. This wasn't just an improved version of classical physics, it was fundamentally different. In quantum mechanics, particles didn't have definite positions and velocities simultaneously. Instead, they were described by wave functions, mathematical objects that gave probabilities for finding particles in various states. The theory seemed absurd, violating common sense at every turn, yet it made predictions of stunning accuracy. For magnetism, quantum mechanics revealed something remarkable. Electrons didn't just orbit atomic nuclei. They also possessed an intrinsic property that acted like a tiny spinning motion, even though electrons weren't actually spinning like little tops. This property, called spin, was purely quantum mechanical, with no classical analog. And crucially, spin generated a magnetic field. Every electron acted like a miniature bar magnet with a north and south pole. The discovery of electron spin came in 1925, emerging from experiments by Otto Stern and Walter Gerlach, and theoretical work by George Uhlenbeck and Samuel Goudsmit. When they sent silver atoms through an inhomogeneous magnetic field, expecting to see a continuous spread of deflections, they instead saw atoms split into two distinct beams. The atoms were acting like little magnets that could only point in two directions relative to the external field, either mostly aligned or mostly opposed. This two-valuedness was completely foreign to classical physics, but fell naturally out of quantum mechanics. Paul Dirac pushed the theory further in 1928, combining quantum mechanics with Einstein's special relativity. His equation describing electrons automatically predicted spin without it needing to be added as an extra assumption. Even more remarkably, it predicted the existence of antimatter, particles identical to electrons, but with opposite charge. When physicists discovered the positron a few years later, exactly matching Dirac's prediction, it seemed like quantum mechanics might indeed be the correct language of nature, however strange its pronouncements. Armed with quantum mechanics, physicists could finally explain why some materials were magnetic and others weren't. In most atoms, electrons paired up with opposite spins, canceling out their magnetic effects. But in elements like iron, cobalt, and nickel, certain electrons remained unpaired, each contributing its magnetic moment. That still wasn't enough for ferromagnetism, though. Individual atomic magnets don't automatically align. In most materials, they point randomly, canceling each other out overall. Werner Heisenberg made the crucial insight in 1928. He realized that quantum mechanics created an effective force between neighboring electron spins, encouraging them to align in the same direction. This exchange interaction arose from a subtle interplay of electrostatic repulsion and the Pauli exclusion principle, which prevented electrons with the same spin from occupying the same space. The details were mathematically complex, but the result was clear. In materials like iron, the exchange interaction favored parallel alignment of spins across many atoms, creating the cooperative ordering needed for ferromagnetism. Temperature played a critical role. Thermal energy jostled atoms randomly, fighting against the alignment tendency. Below a critical temperature, now called the Curie temperature, after Pierre Curie's earlier experimental work, the exchange interaction won. Iron spins lined up. Above that temperature, thermal chaos triumphed, destroying the magnetic order. Iron's Curie temperature sat around 770 degrees Celsius, which explained why blacksmiths had discovered centuries earlier that heating iron destroyed its magnetism. Even with aligned atomic magnets, another puzzle remained. Why did iron magnetize so easily while requiring relatively weak fields to change its magnetization if all those atomic magnets were locked together by exchange forces? The answer involved magnetic domains, regions within a material where all spins pointed the same direction, but different domains pointed different directions, so a piece of iron could contain countless tiny magnets canceling each other out. An external field didn't rotate individual atomic spins much. Instead, it moved domain boundaries, so growing domains aligned with the field while shrinking oppositely aligned ones. This domain picture, developed mainly through the work of Pierre Weiss in the early 1900s and later refined by quantum mechanical understanding, explained both the ease of magnetization and hysteresis effects. The existence of domains raised its own question. Why didn't all the spins in a piece of iron point the same way, minimizing exchange energy? The answer involved competing energy contributions. Creating domain boundaries cost energy, since spins had to twist from one direction to another. But having all spins parallel created enormous magnetic field energy extending into space around the material. Dividing into domains reduced that external field, saving energy overall. The actual domain pattern in any sample represented a delicate balance between these competing factors. As physicists developed better tools for studying magnetic materials, they discovered an astonishing variety of magnetic behaviors. Some materials, called anti-ferromagnets, had spins that alternated up-down, cancelling perfectly with no net magnetization, yet exhibiting distinctive properties different from ordinary non-magnetic materials. Louis Néel predicted this behavior theoretically in 1936 and received the Nobel Prize decades later when experiments confirmed these strange, magnetically ordered yet non-magnetic materials existed. Even weirder were ferrimagnets, where spins pointed in opposite directions but didn't cancel completely, yielding a net magnetization smaller than if all spins aligned. And some materials showed helical magnetic ordering, with spin directions rotating gradually through the crystal. Others exhibited complex patterns that changed with temperature, transitioning through multiple distinct magnetic phases. The variety seemed endless, each new material system revealing nature's creativity in arranging quantum mechanical spins. Applications followed understanding. Recording information using magnetic materials became possible once physicists understood how to create materials with stable magnetic domains that could be switched reliably. The invention of magnetic tape in the 1920s and magnetic hard drives in the 1950s revolutionized data storage, eventually enabling the digital revolution. Every bit of data stored magnetically represented a tiny region with spins pointing one direction or the other, encoding 0 or 1. The ability to pack more bits into smaller spaces drove technological progress for decades, requiring ever deeper understanding of magnetic materials and ever more precise control over their properties. Medical applications emerged too. Magnetic resonance imaging, developed in the 1970s and 80s, exploited the magnetic properties of hydrogen nuclei in the body. By applying carefully controlled magnetic fields and radio waves, doctors could make these nuclear spins wobble and emit signals that revealed the distribution of water and fat in tissues. The technique provided detailed images of internal organs without radiation, transforming medical diagnostics. The underlying physics traced directly back to quantum mechanics and the magnetic properties of spinning particles. Meanwhile, physicists continued probing deeper into quantum effects. Superconductors, materials that lost all electrical resistance below certain temperatures, also expelled magnetic fields completely, a phenomenon called the Meissner effect discovered in 1933. This perfect diamagnetism arose from quantum mechanical currents flowing on the superconductor's surface, generating fields that precisely cancelled any applied field inside. The phenomenon demonstrated quantum mechanics operating on macroscopic scales, with electrons pairing up and condensing into a single coherent quantum state extending throughout the material. The late 20th century brought another revolution with the discovery of quantum Hall effects. When electrons were confined to two-dimensional layers, cooled to extremely low temperatures, and subjected to strong magnetic fields, bizarre things happened. The electrical resistance didn't vary smoothly with field strength, but jumped in discrete steps, taking values determined by fundamental constants with astonishing precision. This quantization reflected topological properties of the quantum states, introducing mathematical concepts from abstract geometry into condensed matter physics. Magnetic fields proved essential for revealing these quantum effects. The field forced electrons to move in circular orbits, quantizing their energy into discrete levels called Landau levels. When the number of electrons divided evenly among available Landau levels, special magic happened, creating robust quantum states unlike anything in ordinary materials. The fractional quantum Hall effect, discovered in 1982, it showed electrons acting collectively as if they'd split into pieces with fractional charge. The physics involved was so exotic that understanding it required entirely new theoretical frameworks. Practical applications of quantum magnetism started emerging. Giant magnetoresistance, discovered independently by Albert Fert and Peter Grunberg in 1988, showed that layered magnetic materials change their electrical resistance dramatically depending on whether adjacent magnetic layers aligned parallel or antiparallel. This effect, arising from quantum mechanical interference of electron waves with spin-dependent scattering, proved perfect for reading data from hard drives. Implementing it boosted storage densities dramatically, enabling the explosion of data-intensive computing. The discoverers received the Nobel Prize in 2007. Spintronics emerged as a field dedicated to exploiting electron spin, not just charge, for information processing. Traditional electronics ignored spin, using only the flow of charged electrons to perform computations. Spintronic devices used both properties, potentially allowing faster, lower-power computing. Researchers learned to generate spin-polarized currents with more electrons spinning one direction than the other, inject these currents into materials, and detect the spin states. Magnetic tunnel junctions became practical devices, with thin insulating barriers separating magnetic layers, their resistance depending on relative magnetic orientations. The quest to build quantum computers brought magnetic considerations to the forefront again. Quantum bits, or qubits, could exist in superpositions of 0 and 1 simultaneously, unlike classical bits that were definitely one or the other. Many proposed qubit implementations involved magnetic properties, electron spins in quantum dots, nuclear spins in molecules, magnetic flux trapped in superconducting loops. Manipulating these quantum magnetic states with exquisite precision became a central challenge, requiring control over individual atomic scale magnets while protecting them from environmental disturbances that would destroy quantum coherence. Throughout this journey from ancient lodestones to quantum computers, certain themes recurred. First, progress came from interplay between experiment and theory. Observations posed puzzles that demanded explanation. Theories made predictions that required testing. Sometimes experiments confirmed theories spectacularly. Other times, they revealed limitations, enforcing theoretical revision. Neither approach alone sufficed. The back-and-forth dialogue between seeing and understanding drove progress. Second, mathematics proved indispensable. Qualitative descriptions could go only so far. Faraday's physical intuition about fields was profound, but Maxwell needed equations to make it precise and reveal unexpected consequences like electromagnetic waves. Quantum mechanics seemed absurd when described in words, but its mathematical formulation made predictions of incredible accuracy. The universe apparently operated according to mathematical principles, and discovering those principles required mathematical tools. Third, each answer generated new questions. Gilbert established magnetism as a natural phenomenon worthy of scientific study, but couldn't explain what magnets actually were. Ørsted and Faraday revealed deep connections between electricity and magnetism, but couldn't explain the mechanism. Maxwell unified the phenomena mathematically, but couldn't explain atomic magnetism. Quantum mechanics explained atomic magnetism, but revealed stranger phenomena like quantum Hall effects. Each layer of understanding exposed deeper layers needing explanation. Fourth, understanding enabled technology. Compass navigation became reliable once people understood magnetic declination and variation. Telegraph systems became practical after Faraday demonstrated induction. Radio communication followed from Maxwell's prediction of electromagnetic waves. Data storage exploited domains and quantum mechanical exchange forces. This pattern wasn't coincidental. Scientific understanding revealed what was possible and how to achieve it, transforming abstract knowledge into practical capability. The story also illustrated how scientific understanding evolved. Early explanations often invoked mysterious fluids or forces, entities that supposedly existed but whose properties remained vague. Gilbert's magnetic effluvia, the electric and magnetic fluids of the 18th century, Coulomb's action at a distance forces, these were stepping stones, better than mystical explanations, but still unsatisfying. Faraday's field concept marked progress, attributing reality to the medium rather than invisible fluids. Maxwell's equations made fields mathematically precise. Quantum mechanics revealed fields as made of particles, photons for electromagnetic fields, while particles possessed wave properties. Each stage replaced vague concepts with more precise, testable ideas. Yet mysteries remained. Even today, physicists don't fully understand high-temperature superconductivity, discovered in 1986 in ceramic materials that became superconducting at temperatures once thought impossible. The mechanism involves magnetism and quantum mechanics, but the details remain controversial despite decades of intensive research. Quantum spin liquids, theoretically predicted states where spins remain disordered even at absolute zero temperature, continue to challenge experimentalists trying to create and characterize them. The quantum nature of magnetic fields itself raises deep questions. In quantum field theory, developed throughout the mid-20th century, magnetic fields arise from exchanges of virtual photons between particles. But what's really happening when magnets attract or repel? The mathematical formalism works beautifully, but the physical picture remains obscure. Some physicists argue that asking for a picture beyond the mathematics is misguided, that the equations are the reality. Others insist there must be some deeper understanding waiting to be discovered. Recent decades have brought new experimental capabilities that would astound previous generations. Scientists can now manipulate individual atoms, placing them precisely on surfaces to create artificial structures. They can measure magnetic fields from single electron spins. They can create exotic quantum states that exist for only fractions of a second before decoherence destroys them. They can simulate materials that don't exist naturally, exploring theoretical predictions impossible to test otherwise. These capabilities open new territories for investigating magnetic phenomena. One emerging area involves magnetic skyrmions, tiny swirling patterns of magnetization that behave like particles despite being collective arrangements of many spins. These structures, predicted theoretically decades ago but only recently created and controlled experimentally, might serve as information carriers for future spintronic devices, offering stability and low power consumption. Understanding and manipulating them requires combining quantum mechanics, topology, and material science, illustrating how modern magnetism research spans multiple disciplines. Another frontier involves quantum entanglement of spins, where particles become correlated in ways that can't be explained classically. Einstein famously called this spooky action at a distance and thought it revealed a problem with quantum mechanics. But experiments consistently confirm these quantum correlations exist. Now researchers explore using entangled spins for quantum communication and quantum sensing, measuring magnetic fields with sensitivities approaching fundamental limits set by quantum uncertainty. The connection between magnetism and fundamental physics continues deepening. In particle physics, every fundamental particle possesses a magnetic moment related to its spin. Measuring these moments with extreme precision tests, theoretical predictions from quantum field theory. Recent measurements of the muon's magnetic moment, for instance, show slight disagreement with calculations, potentially indicating unknown particles or forces not included in the current standard model of particle physics. The centuries-old study of magnets thus connects to the most fundamental questions about nature's building blocks and forces. Cosmology and astrophysics also involve magnetism crucially. Magnetic fields pervade space, from Earth's protective magnetosphere that shields us from solar wind to enormous fields threading through galaxies and galaxy clusters. The origin of cosmic magnetic fields remains partially mysterious. How did they first arise? How do they get amplified to the enormous strengths observed around neutron stars and black holes? Answering these questions requires understanding magnetism in extreme conditions where classical intuitions fail. Earth's magnetic field itself continues revealing surprises. The geodynamo that generates it through fluid iron flows in the outer core is understood in broad outline, but details remain murky. The field reverses polarity irregularly, with north and south magnetic poles switching on timescales of hundreds of thousands of years. But the timing seems random, and the reversal process itself remains poorly understood. Recent measurements show the north magnetic pole currently moving rapidly across the Arctic, and some data suggest the field might be weakening, possibly indicating a coming reversal. Understanding these changes requires combining geophysics, fluid dynamics, and electromagnetism. Looking forward, quantum technologies might transform computing, communication, and sensing. Magnetic materials and phenomena will likely play central roles. Topological insulators, materials that insulate in their interior but conduct electricity on their surface with special quantum properties, might host robust qubits, Majorana fermions, Exotic quantum states predicted to exist in certain superconductor magnet hybrid systems might provide even more stable quantum information storage. These possibilities drive intensive research worldwide. The story of magnetism illustrates how science progresses. It's not a straight march toward truth, but a complex journey with wrong turns, lucky accidents, bitter disputes, and stunning insights. Gilbert thought magnets possessed souls. We know they don't, but his careful experiments established magnetism as a natural phenomenon. Ørsted stumbled upon electromagnetism by accident. I but recognized the significance immediately. Faraday, lacking mathematical training, developed physical intuition that mathematicians took decades to formalize. Maxwell, seeking to express Faraday's ideas mathematically, discovered something Faraday never imagined: electromagnetic waves. Quantum physicists revealed that everything we thought we knew about reality was wrong, yet their bizarre theory made predictions confirmed to extraordinary precision. Each generation built on previous work while overturning previous assumptions. Gilbert used Aristotelian concepts of natural motion and tendencies. Ørsted and Faraday worked within Newtonian physics of forces and matter. Maxwell's equations seemed the final word, expressed in the language of fields. Then quantum mechanics revealed that fields were made of particles, and particles behaved like waves, forcing a complete reconceptualization. Today's quantum field theory would be incomprehensible to Maxwell, yet it includes his equations as a special case. This pattern likely continues into the future. Our current understanding, however satisfying it seems, probably contains assumptions that will be overturned. Quantum mechanics and general relativity, our two great theoretical frameworks, are inconsistent with each other. Somehow they need unification, perhaps through string theory or loop quantum gravity or something not yet imagined. That unification might reveal magnetism in an entirely new light. Yet despite revolutions in understanding, certain facts remain. Magnets attract iron. Opposite poles attract, while like poles repel. Electric currents create magnetic fields. Changing magnetic fields induce electric currents. Moving charges experience forces in magnetic fields. These phenomena, observed for millennia or centuries, persist regardless of how we explain them. Our theories change, improving and deepening, but the phenomena remain. Nature doesn't care how we describe it. The progression from mystical explanations invoking souls and sympathies to precise mathematical theories involving quantum spins and field quanta represents one of humanity's great intellectual achievements. Starting from simple observations accessible to anyone, magnets sticking to iron, centuries of careful experiments and creative theorizing built an edifice of understanding that explains everything from how compass needles point north to how data stores on hard drives to why atoms don't collapse. The same phenomena that puzzled ancient Greeks now form the foundation for technologies they couldn't have imagined. What made this progress possible? Partly it required rejecting supernatural explanations and insisting on natural causes that could be investigated systematically. Partly it needed careful experimentation, isolating phenomena, and measuring them precisely. Partly it demanded mathematical formalization, expressing relationships quantitatively rather than just qualitatively. So partly it involved lucky accidents and unexpected observations that opened new directions. Mostly it required brilliant individuals asking the right questions and pursuing answers with persistence despite obstacles. Yet individuals worked within communities and traditions. Gilbert built on Gilbert de Colchester and other predecessors. Ørsted knew about Volta and Galvani. Faraday learned from Davy. Maxwell studied Faraday and previous mathematicians. Quantum physicists inherited centuries of accumulated knowledge. Each breakthrough depended on prior work, equipment, and techniques developed over time, and communities that valued and supported research. Science is a collective human endeavor, not just individual genius. The story reminds us that knowledge is hard-won. Progress isn't inevitable or automatic. It requires resources, institutional support, freedom to question accepted ideas, and cultural values that prize understanding for its own sake, not just immediate practical benefit. Many of the discoveries discussed emerged from pure curiosity with no obvious applications. Maxwell predicted radio waves decades before anyone thought to use them for communication. Quantum mechanics seemed like pure abstract theory until it enabled semiconductor technology and nuclear power. Today, we face enormous challenges from climate change to disease to resource scarcity. Meeting them requires not just applying existing knowledge, but expanding it, making new discoveries that reveal possibilities not currently apparent. The story of magnetism shows this is possible. Problems that seemed impossibly difficult or even mystical to one generation become solved and routine to the next. But only if we maintain commitment to rigorous investigation, support institutions that enable research, and cultivate the combination of creativity and discipline that science requires. In a broader sense, the magnetic journey illustrates how we make sense of the world. We start with immediate experience. This rock sticks to iron, that one doesn't, and look for patterns. Why do some materials attract? Under what conditions? Can we predict behavior? We form hypotheses, test them, revise them based on results. Gradually, painstakingly, we build understanding. The process never ends because each answer reveals new questions, each solution opens new territories to explore. From lodestones to quantum computers, and from mysterious rocks to precise equations, magnetism's history shows the power of human curiosity and reason. When we observe carefully, think critically, test rigorously, and build on each other's work, we can understand nature's workings with astonishing depth. Not perfectly, not finely, but progressively, continuously deepening our knowledge. The magnets that puzzled our ancestors now illustrate fundamental principles of quantum mechanics and power technologies essential to modern life. What seems mysterious today may be routine tomorrow, if we maintain the commitment to understanding that drove Gilbert, Ørsted, Faraday, Maxwell, and countless others who found beauty in discovering how nature truly works.